Right. Welcome everybody to this week's GOCC. And we're very happy to have Moriah, who's going to be telling us about open quiver loci, CSM classes, and chained generic pipe dreams. Before we begin, let's remind everybody of our community statement. We all are all learning, everyone has something to contribute, and no one has all the answers. So with that being said, Moriah, take it away.
All right, yeah, thank you so much. Thanks to the organizers for the invitation. I want to maybe invite people to ask questions out loud or in the chat. I can't actually see the chat, but hopefully people will let me know when there's something in the chat. And before I get into it, I want to mention that there is a FIPSAC abstract currently posted to the archive. I am hoping to get a full version submitted tomorrow. So keep your eyes out for a full version with all the details if you're interested in knowing more about this stuff. Okay, so outline before we get started. The idea of this is I'm going to start by telling you about some objects that we care about and that I want to study. And the things I'm going to be trying to study about them are certain statistics about these objects in a certain equivariant cohomology ring. These end up being polynomials. So these are certain statistics that I'm going to want to compute that are polynomials. And then the rest of the talk is going to be using combinatorics to compute those polynomials. So a big, big factor is going to be pipe dreams, and then a new version of pipe dreams called chained generic pipe dreams. And if there's time, I'll get into some combinatorial proof ideas. Okay, so to start by telling you about the objects, let me tell you where the objects live, which is in the space of quiver representations of an equioriented type A quiver. So a quiver is just a digraph. Ours being equioriented type A just means that there are one line of vertices and the arrows all point in the same direction. So we're going to look at n plus 1 vertices labeled 0 through n. And the idea here is we're going to fix a sequence of vector spaces, call it V. So V0, V1, all the way through Vn, one vector space for each vertex. And then to each arrow, we're going to assign a map. Call them Phi1, all the way through Phi(n), and the idea is we're going to fix the sequence of vector spaces and look at the space of all possible sequences of maps phi. So that space is going to be our space of quiver representations that we're going to call HOM. It's just a big product of matrix spaces, big affine space. I guess you have to pick a basis for that. And this space has an important action that's just change of basis. So it's this big product of general linear groups of each of the vector spaces. So for instance, this GL of V1 is going to act by multiplication on one side of Phi1 and inverse multiplication on the other side of Phi2 to have the effect on the map of just changing the basis of V1. And this is an important action that people like to consider, kind of naturally comes with this construction. I'll point out that if you've seen quiver representations before, you might be used to thinking about isomorphism classes or isomorphisms of quiver representations. Here, in this sense, two quiver representations are isomorphic if and only if they are in the same GL orbit. Okay. So that's the background space, is the space of type A quiver representations. Let's talk about the actual objects that we're looking at within that space. So to a quiver representation, we can associate something called a rank array, where we just record all of the ranks of maps and compositions of maps of the matrices in our quiver representation. So for instance, here is an A3 quiver, n equals 2, with this fixed sequence of vector spaces. And this is a quiver representation for this quiver. You might notice here that in order for that first matrix to be a map from C to C squared, I'm actually using row vectors here so that the composition agrees with the direction of the arrows. But okay, so this is an example of a quiver representation. Let's write down its rank array. So the, I guess, convention is, or it's important to record along this diagonal, the rank of the identity map at that vertex. So that's just going to be the dimension of the corresponding vector space. Then Along here, we record the ranks of the maps from 0 to 1 and 1 to 2, which is just 1 and 1. And then in this bottom corner, we can record the rank of the composition, which is just 0. So this is a rank array. We have a rank array for every quiver representation. And maybe the natural object to consider here is, let's look at all of the quiver representations with a given rank array. And that is what we're going to call the open quiver locus associated to a given rank array R, is just all of the quiver representations with that exact rank array. And I'll mention here that these are not actually open in the Zariski topology. If you're familiar with the Zariski topology, you know that very few things are really open. So only one of these is actually open. You should think that these are open in the sense of Schubert cells or open Richardson varieties, where they're just not closed. So the closures, we actually have a nice description for, and these are maybe more well-studied historically. So the closures are called quiver loci. And this nice description is we just make the rank conditions weak. We're looking at quiver representations with rank arrays less than or equal to your fixed rank array in every entry. So this is cut out by conditions about determinants vanishing. So it's closed in the Zariski topology. And these are going to be our main objects. These two things, in particular these. So that's the first part. The next question is, what are we going to study about these objects? So our goal is going to be to find certain classes in GL equivariant cohomology associated to each of these things. So what is equivariant cohomology, briefly? In usual cohomology, the idea is that you plug in a space to your cohomology functor, and you end up with a ring. In equivariant cohomology, we're additionally going to take into account this action, in this case our change of basis action on our space of quiver representations, to get a cohomology ring that's richer in some sense. And I'm not going to really tell you what I mean by that. Maybe morally it's about modding out by the group action in some way. But in particular, we can see in this case, hum is this big product of matrix spaces. It's big affine space. It's contractible. Its usual cohomology is not going to be that interesting to find classes in. It's just going to be, if we're taking z coefficients, it's just going to be z in degree 0. So we want something, a ring that gives us more to work with so that we can find more interesting classes associated to each of these two subvarieties. And in fact, this equivariant cohomology ring gives us a lot more to work with. It's going to end up being a certain ring of invariance in a nice big polynomial ring. So we're going to have alphabets of variables, these collections of variables corresponding to each vector space in our fixed sequence of vector spaces. And the number of variables in each alphabet is going to be the dimension of the vector space. And we're going to end up with the polynomials in these variables that are invariant under permuting each alphabet separately within itself. So that's this product of symmetric group invariance. And in examples, I'm going to probably rewrite these as like A, B, etc., instead of the superscripts. And I'll just mention here that behind the scenes, we're computing in equivariant cohomology with respect to the torus inside GL, and tori have weights. So these variables are actually torus weights for this action. So that's what these variables are coming from. But the moral of the story is that these classes are going to be polynomials. So we're looking for polynomials associated to these two things. So the easier one to talk about is the closed thing, the quiver locus. So since quiver loci are closed and GL invariant under this group action, they're going to define classes in Borel-Moore homology that just immediately, kind of through a version of Poincare duality, give you equivariant cohomology classes. And this is maybe not in the equivariant cohomology language, but this is very standard. So people have been studying these things called quiver polynomials, these associated classes, since like the 50s in the context of degeneracy loci. So it turns out that these equivariant cohomology classes can be translated into a question about maps of vector bundles and looking at loci where they drop rank on the manifold below. So it turns out that that computes the same thing, and this is kind of, people call it a universal setting. But the point is, these are really well studied since like the 50s. In 2006, my advisor, Alan Knutson, along with Ezra Miller and Mark Shimozono, were able to give 4 positive combinatorial formulas for these polynomials. So in 99, Buchan-Fulton had a formula, but it was conjecturally positive combinatorial. So they were able to come up with this, and they came up with 4. One of them was in terms of pipe dreams. So I'm going to give you a version of that formula, that pipe dream formula, later in the talk. So that's quiver polynomials. What about the open quiver loci? What can we associate to those? So that requires more machinery, and that machinery didn't exist until Grothendieck and Deligne in 1970 made a conjecture that MacPherson was able to prove existence of, and Emoto extended to invariance in 2006, equivariant cohomology in 2006. A very general version of this, I've written it down here for our specific case. But in general, if we have a invariant subvariety for our action on our larger space, we can naturally associate an element of equivariant cohomology. And this naturally means that it's coming from a natural transformation. I'm happy to discuss that more later if there's interest. But there exists a natural transformation that gives us an equivariant cohomology class associated to any subvariety. It doesn't necessarily need to be closed. That's going to be important for us figuring out classes associated to this. The other wrinkle here is that for our purposes, we're going to consider an extra C-cross action, so an extra torus action. And this torus action is not going to do anything too interesting. It's just going to scale the tangent fibers with weight h bar and do nothing to Hom itself. And the point of this is, so in the same way that we got a polynomial ring from the torus in GL, we're going to get just an extra variable in our polynomial ring from this extra torus. And that's just going to be kind of, the convention is weight h bar. And the point of this h bar is just to make the polynomials that we end up with homogeneous. So it really doesn't add any extra information. It just makes sure that we're looking at homogeneous elements of equivariant cohomology, rather than a total Chern class. If you're familiar with those are inhomogeneous. So here we can look at this base case. So this was come up with in the general context by Grothendieck and Deligne to make sure that they weren't asking for something trivial. So in the base case, if you have a smooth and proper variety and you want to compute the Chern-Schwartz-MacPherson class associated to the entire thing, the base case in their setting was that it was the total Chern class of the tangent bundle. Here, we want it to be the equivariant Euler class of the tangent bundle. And yeah, I mean, like I said, the only difference there is that we're making it homogeneous. Okay, so this makes this thing non-trivial, and these are actually really nice and good polynomials to compute. Why is that? Well, first of all, they're additive under disjoint union. That's really important for computations and for proofs of theorems that you're going to see. This is an important fact about them. And then also, this Chern-Schwartz-MacPherson class of a given variety is going to include, since it's not homogeneous if you ignore h bar, it's going to include the data in its top degree of top polynomial degree in these variables of the Euler characteristic of your variety. So that really requires it being able to see something past the closure, right? If you remove a point, that's going to change the Euler characteristic, but not going to change the closure. And it also contains the data of the cohomology class of the closure of the variety. So that appears in the bottom degree if you ignore h bar, or the coefficient of the highest degree of h bar. So in particular, what this means is that the Chern-Schwartz-MacPherson class of the open quiver locus contains the data of the quiver polynomials. So if we want to compute quiver polynomials, we can compute these Chern-Schwartz-MacPherson classes of these instead, and that's more information. Okay, I think this is a good place to pause for questions if there are any. After this, I'm going to talk about combinatorics and the combinatorics colloquium.
Sorry, may I ask how I should think of GL equivariant cohomology? I'm somewhat confused because it's an infinite huge group. It's not like gluing together a few points.
GL is a huge group?
I mean, usually.
Yeah. So it turns out it's kind of a, it turns out that GL equivariant cohomology is the same as Borel, like take B plus upper triangular matrices, equivariant cohomology. And it turns out I think it's because it's smooth and it has finitely many T fixed points, it turns out that it's the same thing as T equivariant cohomology. So it turns out, or sorry, not same thing. It turns out that it injects into T invariant cohomology.
I see. Is this like one of those GKM models where it's like a spline on something?
I'm not sure. I've heard those words before, but I'm not sure. The way I think about it is like the Borel construction. So for a torus, it turns out that you can turn it into the usual cohomology of CP infinity. So for a torus, you get a polynomial ring, and then there's some nice machinery that lets you embed into a polynomial ring in nice cases. Another maybe good thing to consider is that a lot of the time, I guess in this case in particular, we can set all of the equivariant variables equal to 0 and get back usual cohomology. So there's always a map in that direction, but I think it's not necessarily. Okay. So I guess, right, so what I mean by this is if we set all of our extra variables to 0, we just get Z, which is cohomology ring of Hom, because
because Hom is a vector space, yeah.
Yeah.
Okay, thank you.
Cool.
Could I ask you, hi, Moriah, this is Peter Webb here.
Hi.
Hi. So you've got these CSM classes going for a GL action on a variety, but are they defined in greater generality? Like yes. You could have like any group acting on a variety, or
so I think, oh boy, I need to remember the words. I think it's linear reductive group. I could be wrong about that. But it's stated in much more generality. I was kind of trying to make the decision when I was writing this talk, do I do the general construction? I ended up deciding against it, but I am happy to talk more about the general construction. Yeah. I probably will in the Minnesota seminar.
Yeah, very good. Thank you.
Yeah. Okay. I will move on. Okay, so now we're going to talk about pipe dreams as our first tool for computing quiver polynomials. So these were come up with by Bergeron and Billy in 1993 for computing Schubert polynomials. So what is a pipe dream? Well, it's a D by D grid of two types of tiles. We have bump tiles and cross tiles. In particular, I want to point out that these bump tiles are really just this tile. We can't rotate it. It's not allowed to do something like this. So two types of tiles exactly. The condition for being a pipe dream for a specific element of the symmetric group is that we're going to think of this grid of tiles as a grid of pipes, and we're going to require that the pipe that enters in row I has to exit from column W of I. So that's being a pipe dream for a particular word. And we also require, or I guess element of a symmetric group, not word. And we also require that no cross tiles appear on or below the anti-diagonal. So this kind of ends up looking like kind of just a sea of bump tiles waving down here. So people generally don't draw that. And then there's this extra condition of being reduced. It's reduced if every pair of pipes crosses at most once. So let's do an example for 2, 1, 4, 3. So here, the top pipe needs to leave out this column 2. In the first row, needs to leave out column 2. And there's only one way for it to do it. It has to go straight across here and then bump up here. And that tells us what the rest of the tile has to look like. This has to be a cross tile, and this has to be a bump tile. Okay, and then same thing for 1. This has to be a bump tile. And then also we know that along the anti-diagonal, we have to have bumps like this. And I'm not going to draw the ones below. Okay, and now for the last few tiles that we need to fill in, we know that pipes 3 and 4 need to cross each other at some point. They can't cross twice, so they can't cross all 3 times. Even though that would give you the right permutation, that wouldn't be reduced. So we can just pick a place for them to cross and fill in the rest with bumps, and that's an example of a pipe dream. And as you might expect, those are the 3 reduced pipe dreams for this particular permutation. Okay, so these are the combinatorial objects. And we're going to assign, I guess, in order to compute polynomials using pipe dreams, we're going to assign pipe dreams a weight. So the way you should think about this is we're going to label the rows and the columns so that this weight of a cross tile is row label minus column label. So we get kind of a polynomial factor if we have a cross tile, and all of the bump tiles we just ignore. Those are weight 1. And it's a theorem of Fomin and Kirillov in 1996 that this is a T-equivariant Schubert class in the flag variety. And this is the connection for us to equivariant cohomology. So this is a way to compute a double Schubert polynomial. And it means that we're computing a class in equivariant cohomology. There exists actually a map called the Zelevinsky map, pioneered by Zelevinsky, that I guess connects quiver loci in Hom to Schubert varieties in the flag variety. So that's what's happening behind the scenes. That's why pipe dreams are coming up, is we are turning our quiver loci and quiver loci into Schubert varieties, sort of, open quiver loci into Schubert cells, sort of, and that is why we are starting to be able to compute using pipe dreams. That's behind the scenes. Okay, so this is how we can get polynomials from pipe dreams. And let's see how to adapt them to our setting. So in the context of quiver loci, it turns out that what we want to look at is block pipe dreams. And there's a mysterious permutation, Z of R, that I'll tell you about at the end if there's time, but for now, there's some way of taking a rank array and getting a permutation out of it. We're looking at block pipe dreams for this particular permutation, Z of R. This one that we computed before is actually Z of a rank array. And we're going to look at a block structure on these pipe dreams. And what I mean by that is we're going to put square blocks around along the anti-diagonal corresponding to the dimensions of the vector spaces. So here, these white kind of squares are of size 1 by 1, 2 by 2, and 1 by 1. That means they're coming from a sequence of vector spaces C1 to C2 to C1. So we're looking at a block structure. And there's a further definition. We're going to use this block structure to kind of simplify our computations a bit. So now we're only going to look at not only disallowing crosses on the actual anti-diagonal, but also the block anti-diagonal. So that means that we're going to not want to consider this pipe dream. And maybe a hint that we shouldn't have needed to worry about it is if you look at the row minus column weight that I was talking about for this particular pipe dream, we're going to end up with this factor. I guess I kind of covered it up, but we're going to end up with this cross tile here that gives us a factor of B1 minus B1. So this weight shouldn't factor in. And I want to mention here that the original pipe dream formula for quiver polynomials in that Knutson-Miller-Shimozono paper doesn't include this reduction. So this is kind of the extra cancellation that I'm contributing. And the proof that I have is geometric. So I would be curious to know if there is good combinatorial reasons for this cancellation always happening on the block antidiagonal, because it frequently look a lot more complicated than just the weight is literally 0. So it can look like several pipe dreams canceling each other out. Anyway, this is the collection of pipe dreams that we want to consider is disallowing crosses on the block antidiagonal. I need to tell you about one more ingredient before I give you the quiver polynomial formula. So we can come up with a maximal rank array given a sequence of vector spaces. Let's just have all of the maps keep as high of a dimension as they can for as long as they can. Well defined, and in particular, the quiver locus associated to this maximal rank array is exactly looking at all of the quiver representations with rank arrays less than or equal to the maximal rank array, which is just all of them. So this is the maximal quiver locus, and it's just telling you you are a quiver representation if you're in there. And if you do this process and you look at Z of Hom or Z of R Hom, it turns out that you always end up with exactly one pipe dream, and the structure of it is going to be entirely bumps below this gray space and entirely crosses above it. So this is above the block super antidiagonal. This has to do with the rota diagram being exactly this. And the other nice thing is that any other Zelevinsky permutation, any other pipe dream for any other Zelevinsky permutation or Z of R for another R, is going to have this solid block of crosses in it. The point of that is that this is kind of a trivial condition that we're imposing, that we just are coming from a quiver representation. So if you are imposing certain rank conditions, that should imply that you are a quiver representation and have these cross conditions. So the formula ends up being, we're looking at, to compute this quiver polynomial, we're looking at all of the reduced pipe dreams for our particular Zelevinsky permutation Z of R associated to our rank array. We're only looking at those without crosses on the block, antidiagonal, and we're going to end up wanting to get rid of the crosses above the block super antidiagonal. So what this symbol means is we just ignore those weights. We don't consider them. They don't actually give us any new information. So here's the example. So turns out that this permutation we've been looking at is the Zelevinsky permutation for the rank array that we computed at the beginning. And let's compute the quiver polynomial. We're ignoring both of these. So on the left, we get row minus column. We get B2 minus C. And then on the right, we end up with A minus B2. So this quiver polynomial is A minus C. All right. So that's the quiver loci. That's kind of the end of the story. I'm going to tell you about quiver polynomials. Well, mostly. For now, let's move on to the open quiver loci, unless there are any questions.
Sort of on topic question. Feel free to just say it's beyond the scope of the talk, but
Okay.
what happened? Do you know what happens if you sum over like all pipe dreams, like not just reduced ones? Does that like have any significance?
Oh, that's the perfect question to ask.
Oh, great. Definitely not planted.
Yeah, no, not planted at all.
Oh, wow.
So
Okay.
yeah, so the reason that the reduced pipe dreams are necessary for the previous, like for I don't know, Schubert polynomials and other pipe dream computations is because the place that you get these pipe dream diagrams from is called the AJS-Billy formula, and it's a formula in terms of, I mean, it's a formula for restrictions of Schubert classes that talks about reduced words. It's like summing over reduced subwords of some larger word that corresponds to all of the places above the block antidiagonal. So that formula includes reduced words. Cheng-Jan Su in 2018 constructed, or I guess proved a formula to compute analogous things about Chern-Schwartz-MacPherson classes for Schubert varieties, or I guess Schubert cells. That does not require any reduced condition. So that's why we end up not requiring the reduced condition. In this case, we're ending up summing over all pipe dreams. We still have the no crosses on the block antidiagonal condition. So also we're gonna look at not only one permutation now, not only just that Z of R, we're gonna kind of look at the block ranks of Z of R, so the number of ones in each block of Z of R, and look at all possible permutations and look at all pipe dreams for all of those permutations. And then we also need to kind of count, this is essentially, well, okay, you'll see what it is later. We're going to need to count a factor of h bar also to make sure that everything's homogeneous, because for instance, we can have more cross tiles or fewer cross tiles now. Because we're not making this reduced word condition, we're also varying the permutation. Our polynomial is not going to be homogeneous anymore. So we need to add this h bar to make it homogeneous. But anyway, using this Cheng-Jan Su formula, we can show that the Chern-Schwartz-MacPherson class of this open quiver locus is this. And it's kind of a messy formula. It's messier than the quiver polynomial formula. And the reason that it's messy is that the pipe dreams keep too much information. We really only care about block ranks, like we really only care about the blocks of the permutations. We don't care about the actual permutation itself, and that means that we need to do this sum over permutations. We also have this extra weight and this cancellation, and it's just a little bit unwieldy. We can still use it to compute, but so for instance, here, even in this small example, we needed a permutation that was different from the original one. Notice it's not because of the reduced condition that we can't have this like all three here. It's because we're not allowing this cross on the block antidiagonal. So that still cancels. But okay, so we can compute using this, but we can do better. So to tell you the right object to think about here, I need to define laces. So it's a tiny part of Gabriel's theorem in 1972 that up to the GL action, or in his statement, up to isomorphism, the indecomposable representations of a type A quiver look like laces. So we call these laces, they're chains of isomorphisms of one-dimensional vector spaces going from vertex P to vertex Q and zeros everywhere else. So this is characterizing these isomorphism classes of indecomposable representations, and it is a fact that maybe I'll try and convince you of a little bit, that the open quiver loci are just exactly these isomorphism classes. They're exactly the GL orbits. And in particular, what that means is that every open quiver locus is going to contain exactly one representation that looks like a direct sum of these exact laces for some array. Here I'm not thinking about the order that we're considering the laces in. We're just fixing this lace array, and we're saying it's equivalent data to a rank array. So the number of laces from P to Q is what this data records. So let me convince you of this by recovering a lace array from a rank array. So I think the best way to do this is to use a lacing diagram. So these were come up with by Abeasis and Delfra in 1985. The idea here is that the vertices are going to be our basis vectors of every vector space in our quiver representation. So 1, 2, and 1 dimensional corresponding to our representation there. And then we're going to draw lines for these summands, these laces. So how do we do that? Well, okay, so this rank array along the diagonal is just telling us the number of vertices. Along here, this first one is telling us that we need a lace there. We need a line segment there. We need an isomorphism of one-dimensional vector spaces there. Notice it didn't matter whether I drew this or whether I drew this because I'm not caring about horizontal permutations here. But here it does matter because whether I draw this or I draw this, these are different isomorphism classes. And the way to figure out which one it is you look at this bottom entry and you say, okay, it can't be this because if it were, then the composition of these two maps would have rank 1. So in fact, it needs to look like this. And then to write down the lace array, we can just count the number of laces in this diagram. So no vertices are all by themselves. We have 1 from 0 to 1, 1 from 1 to 2, and none from 0 to 2. And my claim is that you can do this in general. There's kind of a just polynomial, or I guess, relation that you can invert to see this. Okay, so these are lacing diagrams, and these are the key ingredient for this generalization of, or version of pipe dreams that we're going to use to compute these Chern-Schwartz-MacPherson classes in a better way, maybe. So what are these chain generic pipe dreams? So first of all, they're not just rectangles like usual pipe dreams, or squares like usual pipe dreams. They have this funny shape that's n+1 rectangles, 1 per vertex, chained from the northeast to the southwest, so 0th, 1st, and 2nd rectangle. And the dimensions are going to be determined by, I think I wrote at some point, these are the dimensions of the vector spaces at vertex I and vertex I+1. So we can kind of read this off, for instance. Since the 0th rectangle has height 1, the 0th vertex has to have a copy of C1. Since the first rectangle has height 2, we end up with a copy of C2, and then the second one has height 1. Note that this one has height 1 and width 0, which is our I+1 for, or R3 in this quiver that doesn't have a third vertex. Okay, so this is the shape of them. Let's talk about the pipes. So we want our pipes to enter from the right of the diagram and leave from the left. So every right side of a tile is going to have a pipe entering. If they leave from the left side of the diagram, they exit the diagram permanently, and if they leave from the bottom, they're going to continue due southwest and enter again. So for instance, I could have a pipe entering here, and I guess an extra condition is that they're only allowed to travel using pieces of usual pipe dream tiles. So they're only allowed to do this elbow, this line, or that line. They can bump each other, they can cross each other, that's fine. But they're only allowed to use these pieces individually. So, I don't know, let's draw a pipe. Maybe it goes across here, maybe it bumps down there, now it continues due southwest, and then maybe it just decides to leave the diagram permanently there, for instance. Okay. Now let's talk about what it means to be a chain generic pipe dream for a particular rank array R. The point is, our requirement is that the pipes are going to resemble the lacing diagram for R. We're going to have a pipe corresponding to each lace. What that means is the number of pipes that appear in rectangle I and in rectangle J and in all of the ones in between and none of them outside is going to be exactly Sij. This is why I need this extra little width 0 rectangle down there. So maybe let's see what that says in this case corresponding to this lacing diagram. So this pipe corresponds to this lace because it appears in rectangles 0 and 1 and no others. To complete this picture, we might end up doing this. And you'll notice I've given them different colors. We're going to color our pipes based on where they leave the diagram. And we're going to impose a condition that same colored pipes are not allowed to cross. That's going to be kind of a special type of bump when same colored pipes bump. Okay, so let's finish drawing the changed generic pipe dreams for this particular lacing diagram or lace array. So we had another option here where we bumped down in the same place. We could have, instead of leaving immediately, we could have bumped and then left later. We can't go down all the way because then we would have to come out here. But we could have bumped and come out here, and then the pipe entering here would have bumped down and gone out there. That's a valid change generic pipe dream. The other option that we had was we could have bumped down immediately. Now this pipe has no choice but to leave the diagram immediately. And we have a pipe entering here. It has to enter at the right of every tile. And this one has no choice but to bump down because it has to appear in this last width 0 rectangle. Okay, so those are the change generic pipe dreams for this particular lacing diagram, and maybe to drive the point home a little bit, I'll show you, we also have these for the lacing diagram that it isn't. So we have our blue pipe corresponding to the lace that goes through all 3 rectangles, and then this dot just looks like a pipe that appears in only 1 rectangle. Okay, so these are change generic pipe dreams, and we're going to do a very similar thing to what we did before, and assign essentially row label minus column label. So you might have noticed that I've labeled the rows and columns of my change generic pipe dreams. This is really just row minus column label corresponding to these pieces of cross tiles. The bump tiles correspond to a weight of h bar, and then either a same colored bump or a blank tile corresponds to the sum of both of those weights. So this is the weight, the product of these tile weights is the weight of a change generic pipe dream, and then it's a theorem that you sum over the change generic pipe dreams for your given rank array corresponding to the associated lace array, and we end up with this Chern-Schwartz-MacPherson class. So these are the better object to compute with because we've forgotten the unnecessary data of things like the specific permutation. And in particular, we have a more natural indexing object. Like instead of needing to translate to a Zelevinsky permutation that's mysterious, we're just using the lace array, which comes directly from the rank array. It's kind of equivalent data. And I'll do an example here. So same thing we've been working with, we can use this to compute the Chern-Schwartz-MacPherson class of the open quiver locus associated to this rank array. And that ends up being, maybe I'll, I guess, think about this first one. So we have 3 bump tiles. None of them are same colored bumps. So 3 bump tiles gives you an h bar cubed, and then this piece of a cross tile gives you an a minus b2. And you can do the same thing over here. Notice this gives you an a minus b1 plus h bar, the sum of the 2 possible weights. And you end up with this formula. And as promised earlier, you can recover the quiver polynomial from these Chern-Schwartz-MacPherson classes by looking at the coefficient of the highest power of h bar, or you ignore h bar and look at the lowest degree term. And what do you get here? You get a minus b2 from that first term, plus a b2 minus c from the second term, and we end up with a minus c, which, if you'll remember, is what we computed before. Okay, so that's change generic pipe dreams. Any questions before I give you a couple ideas about, maybe you've been noticing already, but I'm going to spell out a little bit more the translation from those original pipe dreams to change generic pipe dreams. All right. So as you may have guessed from my illustrative highlighting, the chain generic pipe dreams are just the block super antidiagonal of our pipe dreams for this like Chern-Schwartz formula. In particular, we don't need any information besides the block super antidiagonal because above it are crosses and below it is the block antidiagonal. So this is because of this analogous to RP star condition, and this is the DHOM condition. And so we know what's happening up here and down here, so we can just ignore it in our diagrams. And that corresponds to requiring pipes to continue due southwest because they're just going to be bumping. We know that for sure. In doing this, we've erased pipes that don't affect the lacing diagram, and I'm going to try and indicate on the next slide why the lacing diagram is relevant, but the point is anything coming from the top is not going to affect the lacing diagram coming from pipes that look like this. So we can erase those. In particular, if we have pipes that we've erased, so a blank tile, it doesn't matter whether those pipes cross or not because it's not going to affect the pipe dream itself is still going to contribute to the lacing diagram. So we can treat this as just both a bump and a cross in that position at once and make this a defined thing with weight the sum of those two weights. Same thing for colored bumps. So if you'll think about that, two pipes of the same color end at the same vertex, correspond to laces that end at the same vertex. It doesn't matter whether they flip which one they connect to or not. So whenever we have a same colored bump, those can always cross and it'll remain a valid pipe dream. Therefore, we can just prohibit them from crossing and make the weight the sum of those weights in the chain generic pipe dreams. Finally, I'll tell you what Z of R is. So the way we get this is Z of R is determining block ranks, but we're requiring that we're going to place the ones in a position to jump rank maximally and as soon as possible. What does that mean? So from our rank array, the definition is that I'm going to put these along the block super antidiagonal. So I guess I'll be more clear. This one corresponds to this one corresponds to this one. The number in the rank array is the number of ones appearing in that block. And because of this maximally as soon as possible condition, we're putting the ones as far left and as far up as we can. The stuff below, so above that, we're just going to do zeros. Below that, we're just going to port in the lace array directly. And that's going to be the number of ones in each of the blocks below, or on and below the block antidiagonal. So you can see we have 0, 1, 0, 1, 0, 1s corresponding to this line, 1 and 1, and 0 here. And now you can think about, we're wanting to consider pipe dreams for permutations with the same block ranks, so we're going to have ones in the same block. And let's look at, for instance, this one right here. This one corresponds in the lacing diagram to this one, which corresponds to this lace from what's going to be rectangle 0 to rectangle 1. In the pipe dream, it corresponds to this pipe to make that permutation. With the point is the one was in this block right here. So there had to be a pipe that started either here or here and came out in this block. And if you think about where that traveled, well, since it came out here, it needs to enter from the right of this first rectangle. So it's going to appear in this rectangle, this 0th rectangle, I guess. And then it has to come down and leave the diagram through this rectangle, the 1th rectangle, the rectangle labeled 1. So since the point of this is since the block ranks come directly from the lacing diagram, they translate to where we can kind of see the pipes in the chain generic pipe dreams. And that's why the lace array is what we're going to end up summing over. It forgets the information about particularly where the ones are. All right, that's all I had. Any questions?
Can I ask you a question, Mara?
Yes.
Oh, good. So I've been wondering, you set up by doing the equi-oriented an plus one quiver,
Yes.
and um, I bet you're prepared for this question. You can probably guess what the rest of my question is. What if you do something else? Like, what if you do a different orientation, or what if you do a different quiver? Like to jump straight to type D might be a bit tricky, and it could be useful for technical reasons to not to work over the complex numbers, but and then to have type B or C, But
Mm,
does this? There must be something pretty similar which works. Like
yeah.
if you do a different orientation, but the combinatorics might look a bit different, perhaps.
Yeah, so the key here is like the key proof technique for all of this is the Zelevinsky map, which talks about specifically the equi-oriented case, but there is a paper, and I'm forgetting the authors, but there is a paper talking about non-equi-oriented quivers. And I will be looking at that shortly. So there is a version of the Zelevinsky map for non-equi-oriented type A that just you end up, so the Zelevinsky map ends up putting you into a larger matrix that is the dimensions of the pipe dreams that we've been looking at. And the equi-oriented case is very straightforward. It just goes along the block super anti-diagonal with identity matrices along the block anti-diagonal. That's the Zelevinsky map. The non-equi-oriented case ends up shuffling it around a bunch, so it's stranger. But I think there's plenty to do there, and that, like I said, that's where I'm going next. The non-type A case, I think, gets a lot weirder because I'm not sure that there is an analog of the Zelevinsky map. So I don't really know of any literature on that.
Yeah. Yeah, like I don't know the way you do, and you have a excellent understanding of it all, but I would have thought in principle like this ought to work. It's just that the combinatorics might get absolutely dreadful, and you have to be drawing different pictures and things. I don't know. But
Yeah,
anyway, yeah.
maybe. I mean, look, okay, at the very least, you can define these things and you can define the quiver polynomials and I mean, uh, I guess maybe the arrays are not quite as nice anymore because you have it's not just you're looking at vertex I to vertex j. You have like maybe different paths you can take. So maybe that's a little bit strange. And then yeah, like it's not going to be necessarily it's like the way to compute these equivariant cohomology classes is the image of a quiver locus is an intersection of a Schubert variety with an opposite Schubert cell. That's yeah, not so hard to compute with. And I don't know what you would end up getting in
Yeah, yeah.
that case.
Thank you.
Yeah.
Question. So if I'm remembering the like Schubert story correctly, if you sort of you're taking the closure of the Schubert cells and you sort of look at the inclusion,
Hmm.
you're getting like Bruja order on permutations, right?
Hmm.
Is there some like if you do that same thing with like the open quiver loci, is there any interest like what's the poset that you get for those
It's
for like the rank
just
arrays?
yeah, it's I mean, so that's like in the if we look at the definition of the rank here. So it's this like uh I don't know the correct word for it, but it's like you need in order for the open quiver locus to be contained in the full quiver the closed quiver locus, you need each of the ranks to be less than or equal to each of the ranks of the closed quiver locus rank array. Does that make
Oh,
sense?
so it's
So
just like
it's
component
just
wise less than or
yeah,
equal to.
comparing each of them component wise. Yeah.
Okay, gotcha. Thanks.
But that does, I think another question I've been asked before is what about CSM classes of the quiver loci? And the answer is, since CSM classes are additive under disjoint union, you get them from the CSM classes of the open quiver loci just by summing up. I haven't looked if there's anything nice there, but I guess the formulas follow.
I guess maybe a follow-up to that. So that you had these mysterious permutations like the Z of R.
Yeah.
Are those related in like Bruhat order if you compare them with like the rank arrays that are?
Hmm. I feel like I should have a fast answer to this, and I don't. Maybe I would guess yes. Why is that? I don't know. I'm not sure. I mean, the construction is based on these kind of block ranks that you're just kind of imposing. I guess, okay, in this case, you could, I guess the other option would be just the full rank array would be, I guess Z hom would be this picture, and this corresponding Zelevinsky permutation would have these two things swapped. So that is a swap.
So that would be less, yeah.
Yeah, I don't know about it in general. Maybe you could do something similar. I don't know.
Thanks. If there aren't any more questions, I will stop the recording.